In this screencast I'm going to look at Rouche's theorem, which I have typed out here for you. It has three criteria that need to be satisfied. The first is that f is analytic on a simply connected region R. F is some function of z that we're given. The second criterion is that gamma is a simple closed contour in R. And the third is that g, which is another function of z, is analytic on R, and that inequality there holds. The modulus of f of z minus g of z is strictly less than the modulus of g of z for z in gamma. And if those three conditions are satisfied, then f has the same number of zeros as g inside gamma. And the application of this theorem is in finding the number of zeros of f, which is can be quite a complicated problem. And what we do instead is we come up with a suitable function g of z, whose number of zeros inside gamma we know, and then we use the theorem to find out the number of zeros of f inside gamma. Let me illustrate this with two examples. Here's the first one. Let's say we have f of z equals z to the 5 plus 3 times z plus 10. And we're asked to say how many zeros f has in the set given here, z modulus of z less than 2. So the question is, how many zeros does f have in S? And so what we do first of all, and I should have said you might want to copy down those three criteria because they're going to disappear off the board in a minute. So if you want to stop the screencast and copy them down first, please do. But I'll proceed. First of all, we define gamma to be a simple closed contour in the region S that we're interested in. And so what we're going to have here is that it's the modulus of z equals 2, so it's just on the boundary there. It's a circle of radius 2. And what we have to do is also define g of z, and this is going to be the dominant term on the contour gamma. And so if we look at f of z, the dominant term is z to the 5. That's going to have the largest value on the contour gamma. So that's going to be my choice for g of z. And notice that we know how many zeros g of z has. It has a 0 of order 5 at the origin. So g of z is a simple function whose number of zeros I know, and therefore that's going to be a suitable choice for me to apply Rouche's theorem. So let me now look at the modulus of f of z minus g of z, and that is f of z minus g of z is just going to be 3z plus 10, the modulus of that. And I now just apply the triangle inequality, and that equals 3 lots of 2 plus 10, which is 16, for z in gamma. So that's my left-hand side of the inequality, and that has to be strictly less than the magnitude of g of z. And that is going to be true because what I've got here is 32. Which is strictly greater than 16. So in other words, all the criteria for the theorem are satisfied, and therefore f has the same number of zeros as g inside gamma, so f has 5 zeros inside gamma, in other words, in the set S that I was given at the start. So that's the first application. I thought I would just give you one more example to illustrate this theorem. A slightly more complicated example. Let's take another function of z, this time 3z plus log of 1 plus z. And I'm wanting to know how many zeros f has inside S, where now S is the modulus of z less than a half. And there's a hint here that I'm going to give you, which is that for z less than a half, the modulus of z less than a half, the modulus of the log of 1 plus z is always less than or equal to 2 times the modulus of z. Now I'll leave you to think about that hint and how it is correct. You can in fact prove it using a Taylor series about 0 for the log of 1 plus z. So you might like to have a go at that and check that you agree with that statement. Because once I've done that, in fact, everything else should follow. What I now have to do is define my gamma. So we'll let gamma equal again the boundary. So we'll take the modulus of z to equal a half. And g of z has to be the dominant term on gamma. And so in this case, in fact, g of z will be 3z. You'll see in a minute that that is a suitable choice, because what I can now do is subtract one from the other, and so I'm just left with the modulus of the log of 1 plus z. And then I use my hint. That is less than or equal to 2 times the modulus of z, which on gamma, the modulus of z is just a half. So I get 2 times a half, which is 1. And if I look at the modulus of g of z, that's 3 times the modulus of z, which is clearly 3 over 2 on gamma, which is greater than 1 on gamma. So all the conditions for the theorem are satisfied, and therefore by Rouche's theorem f has the same number of zeros as g inside gamma, and I've just taken g off the top of the slide slightly, but inside gamma g has a simple 0 at 0, and so f will have 1 0 inside gamma, in other words on S, just as g does. And that ends this second example illustrating Rouche's theorem.